It's my great pleasure to be here. So today I'm going to talk about my research in focusing on understanding blackout mechanism in renewable electricity grid on the climate streams. So before I start, I want to ask the audience a question. How many of you have experienced power outage caused by any extreme events? Please raise your hand. Yeah, well, that's a lot. But thanks. So what if I can tell you the situation is getting worse? So we have it's not working. Yeah. So what if I can tell you the situation is getting worse? And we have the evidence from US recent blackouts. Since the 21st century, over 80% of major US blackouts were weather related. And we saw a 70% increase in this decade compared to the last one. And the Puerto Rico island experienced twice catastrophic blackout, which means that the whole system collapsed, went to 100% blackout. And one is caused by Hurricane Fiona, and the other is Hurricane Maria, with over 100 billion US dollar total damage cost. And at the same time, our grid is under clean energy transition, and we are making our grid more exposed to environments, and with increased interaction with the environment. So also increased uncertainty and the demand variation, because we are integrating more and more solar and wind, and they are intermittent. We can call them they are environment sensitive. So this is a very famous California dark curve. So as the increasing penetration of the solar, so you can see the steep dark curve it will be because of the demand variation, because like the solar only generated during the daytime, and to cope with that, the grid needs more flexible resources. So that's one challenge, and also the situation becomes more severe under extreme events, because the hurricane can bring like a massive cloud structure. For example, here this is normal condition during a Hurricane Hillary in California, 2023. Normal condition, it can generate 14,000 megawatts solar at peak. And during hurricane period, it can only generate 4,000 megawatts. So which means this is a very like a small tropical cyclone, it still reduce 10,000 megawatts solar generation at peak for California grid, almost 1/3 demand, supposed to meet by the solar. So the challenge is that we first face the challenge from climate change, with more intense climate streams like heat waves, tropical cyclones, flood, rainfall. And also we have a challenge from decarbonization by integrating more and more like environmental sensitive renewables like solar and wind. And these two challenges are not independent; they are coupled. That's the reason we're saying we're facing a climate energy superimposed risk. And but this is a necessary path. So because we want to fight against the climate change, and before we can really reverse the warming trend, so we have to go through it. And my research is not advocating against clean energy transition. Rather, we're saying how can we maximize the benefits of clean energy transition and mitigate the associated risk under intensified climate streams. So the first question is my talk want to answer today here is how can we quantify the risk? So to quantify the risk, so basically we want to understand what caused the blackouts. And that's still a huge obstacle to understand blackout mechanism on the extremes for electricity grid. And someone said that quote here, electric power system is one of the largest and the most complete machine human have ever created. The stated quote is we have very few experiments. So basically you cannot find a grid operator, tell them let's trigger blackouts, see whether we can stop it. It's impossible, right? No one will allow you to do that. And all the current theory, the limits to transmission grids and mostly on the common cause failures, not climate streams. So how can we understand the climate stream impacts, and what's the role of increasing renewable and energy storage, integration in energy system resilience, which cannot explain by this current model focusing on common cause failures. So let's look at a real-world event happened in Puerto Rico Island I mentioned before, caused by Hurricane Fiona in 2022. It caused a system-wide blackout. And the reason why it's unique, this is the first, we got the first high-resolution outage data for weather-induced system-wide blackouts in the history of the power systems. So look at the outage map. So you can see at 1750 UTC time, the grid can still supply their electricity service to over 50% customers. But just within 10 minutes, it went to zero, which means grid collapse here. So, our model is trying to figure out what happened here. So we developed a model called climate-induced renewable energy system cascading event model called Crescent. It comprehensively links the high-resolution climate extreme simulation and the multi-layer grid vulnerability across renewable generation, transmission grid, and the distribution grid, and also multi-timescale grid resilience components. So first, we used a physics-based method to simulate high-resolution spatial temporal wind hazard, the wind field here for hurricane. And as an input, so we can test for our grid vulnerability components. We first consider transmission grid vulnerability, including like transmission towers and the transmission lines, they will also like fail, and also the network cascading dynamics. So the network cascading dynamics basically describe the transmission line outage happen. The power flow belong to this line will transfer to other lines and potentially cause other line overloaded, and then the overloaded line will trip again. So this kind of like propagate to the line failure can propagate to the whole grid, affect the whole system stability. And then we also consider the distribution network outage. So we look at their vast distribution networks. And if you just zoom in from here, there's a substation, and we can see like the 3 distribution feeders attached to the substation. It's like the road networks. The grid, even though it's just an island power system, it still has thousands of distributed feeders. So, they are also the most vulnerable components, and has been largely ignored by the previous model. And like the outage of these distribution feeders can cause like the power imbalance between the supply and the demand, challenge the transmission grid operation. That's the reason why we need to consider that. Yeah, and then we also consider the climate extreme impacts on the utility and the distributed solar PV generation. For example, the hurricane the wind has damaged the solar panels, and like the massive cloud structure of the hurricane can significantly reduce the solar irradiance, which reduce the solar generation. And these parameters were fit by using like many historical tropical cyclones along the U.S. Gulf and the eastern coast. So for grid resilience components, for short-term stability, we also consider the grid dynamics under power imbalance. And this is the differential equation for every generator, and we can derive the we call the stability criterion, rate of change of frequency, to this, which serve as like the stability criterion, so we can know whether the system can withstand the power imbalance. And we also consider real-time operations and system flexibility, basically mimic the grid operators' emergency control during any extreme events. Like they will perform load shedding to prevent these cascading failures. So don't worry about the equation here. It's just optimization model. So basically, the grid operator minimizes the load shedding and make sure all these physical constraints, like the line capacity constraint, generation capacity constraint, can be satisfied based on your methods. So using our model, we can generate thousands of realizations for this catastrophic blackout, and considering uncertainty in component hazard resistance. So this is also the first model we can capture this unique event, like I mentioned, it happened in Puerto Rico. So the light blue curves are our simulation, and the dark blue one observed. So you can see the drop here. But the interesting thing is, even because our simulation considers uncertainty in component hazard resistance, which means for one realization, the same component can fail like early, but in another realization, the same component may fail in late stage. So we found like this uncertainty cause a difference in their their like system stability. For example, some of them eventually survive. We call it resilience pattern, and some of them went to 100% blackout. So we are trying to figure out why like the uncertainty in component has a resistance, which means like the failure time of some components can cause such like the difference in the resilience pattern and the vulnerability pattern. So let's look at the critical lines. So the critical lines that will actually identified by a topology concept is called the current flow between its centrality. So basically describe the line has a higher contribution to the grid topology connectivity, and the outage of the line can cause a larger power flow transfer. So we identify 4 critical lines, and then we look at the failure time of these critical lines. And the interesting thing is when we look at the resilience pattern, which means the least realization survive eventually. And then in resilience pattern, these critical lines fail earlier. And the invulnerability pattern and the least critical line fail in later stage. So in another word, which means like the early failures of least critical lines can enhance the grid resilience compared to late failures. So probably it's a little bit hard to understand, but I can give you an analogy. So you probably hear and like the rolling blackouts happen in Texas a lot, right? So the rolling blackouts basically is a proactive strategy to de-energize the grid. So we found that even passively de-energize the grid by like the critical line failure. So we can still enhance the grid resilience. So compared to late failures. So I mean like this is another way to de-energize the grid, because the early failure of this critical line reduce the power flow burden within the grid. Because like the failure of this grid cause power flow transfer, the grid operator will perform like emergency control to reduce the whole level. So which means like it may like the suffer in the early stage, but it like make the system more resilient to ride through the subsequent damage. And we'll considering the higher penetration of the renewables, like the Puerto Rico, aligning with the Puerto Rico Act 17, they want to achieve not only net zero by 2050, that is like the 100% renewable grid by 2050, and the interim goals is 60% renewable penetration. So, and we can consider increasing the behind the meter solar integration, and we found below a certain threshold, that is 45% threshold, including the current penetration level, 16%. So we can see like the renewable integration has minimal impacts on system resilience. But beyond this level, we saw superlinear growth in probability of catastrophic blackouts across that. So what's the solution? So everyone knows like the storages will play a critical role in here. So we consider every 1 megawatt solar paired with 0.5 megawatt and 2 megawatt hour of energy storage, and they operating in a grid forming mode, and which means they can mimic the behavior of the synchronous generators, and we saw that it can, and so it can provide a version inertia to the grid, and we can see here this is without an additional storage. But adding additional storage means parallel storage to solar. We can see like it can alleviate this situation and even make the grid more resilient, even compared to the current condition. So I mean like but the issue is the most current storage installed to the solar panels mostly are not grid forming; they are grid following, and they cannot provide like a kind of virtual inertia to the grid, and they are individually optimized. So I mean, we still have a long way to go, and I saw like that many power electronics experts here, like Professor Chen is here. So and also expert here in power electronics. So I mean, like we hope they can provide more resilience to our electricity grid. Yeah. So let's go to conclusion. So we developed a model called Crescent, validated by historical events. So we're actually working with the local power utility in Puerto Rico they give us their future grid configurations, and we make projections for our for future climate streams. For example, heat waves and tropical cyclones. This is our previous work for U.S. Gulf and Eastern Coast for like heat wave and tropical cyclone. So we can see under higher emission scenario, the situation is getting worse. We have more extreme events and more severe and extreme events. So, and we also developed a method not only quantify risk but to mitigate the risk by developing a risk-aware electricity dispatch model we call reducer. It coordinates the thousand distribution network and the transmission network. So last things I want to thank my interdisciplinary collaborators, Professor Ningling and Vince Poole, and also Andlinger Center Fund for Energy Research with corporate partner and our corporate partner Luma Energy, and also the National Science Foundation. And if you're interested in full story of my research, you can go to check the Andlinger Center's website. Thanks for highlighting our research using this article, helping energy system weather the storm. The interesting thing is they posted one day after they posted, I experienced power outage because like you remember a few weeks ago that thunderstorms. So I mean we still have a long way to go. Thank you.